thanks for watching, and today I would like to talk to you about the exponential derivative of a function. And you might be like, what the hell does that even mean? Well, look, if we have a smooth function, we can differentiate this. So, just a little definition, if I write df, that's f prime. Well, we can continue with that, right? We can do d squared f, which is just d of df, and that's, df prime, and that's f double prime. And we can continue, right? d cubed f, that's f triple prime. And you can continue. In general, we can also define the nth derivative. So dn of f is the nth derivative of f. And you can also define half derivatives, but that's something else. And now the question is, look, we're really good at defining, powers of derivatives. D squared, d cubed, d to the n, whatever. And we can also add them. We can do df plus 2d squared f. It's the same thing. And in particular, because we're really good of doing, polynomials of derivatives, you may guess, well, to define the exponential derivative, just use power series. That's how I came up with this idea. I was teaching about Taylor series, and I was like, oh, well, you could also do Taylor series of exponential. So, remember, we had the Maclaurin series of e to the x is the sum from 0 to infinity of x to the n over n factorial. Well, you can then just define the exponential derivative to be the sum of n from 0 to infinity of d to the n over n factorial. And this is what's called a differential operator. Namely, it's a meta function which takes f as its input and returns the following thing. At each step, you differentiate f n times, and you divide it by n factorial, and you sum up the results. And let's do some examples, and you'll see there's something truly magical that will happen. For example, let's do e to the x. So example 1, let's do the exponential derivative of e to the x. So again, e to the x is the input, and it'll spit out another function. Well, that becomes a sum from 0 to infinity of d to the n, e to the x, over n factorial. And here's the thing, if you differentiate e to the x however many times, you just get e to the x. So you get the sum from 0 to infinity of e to the x over n factorial. E to the x comes out, and you get the sum from 0 to infinity of 1 over n factorial. And then just use e to the x with x equals to 1 to get that this is e, and you get e to the x times e, which is e to the x plus 1. So the exponential derivative of e to the x becomes e to the x plus 1, which is very cute. In other words, it shifts e to the x by 1 unit. So very surprising, but it's cool with this definition. And in fact, let's continue. Now, if we did e to the x, how about e to the kx? So e to the d, e to the kx. That's again sum from 0 to infinity of dn e to the kx over n factorial. And here's the thing, if you differentiate e to the kx, you get k e to the kx. If you do it twice, you get k squared e to the kx. 3 times, k cubed e to the kx. And in general, k to the n e to the kx over n factorial. And again, this doesn't depend on n, so it comes out. So e to the kx, sum from 0 to infinity, k to the n over n factorial. And if you do calculate that, you use the power series of e to the x, but with k, and you get that this is e to the k. And so in this case, you get e to the kx, except with the factor of e to the k. And surprisingly, again, you get that it just shifts the function e to the kx by 1 unit. Very interesting, huh? And in fact, here's the cool thing. K, it can be anything. It could be an integer. It could be a fraction. It could be an irrational number. It could even be a complex number. So if you actually do this with e to the ix, you get the following. So e to the d, e to the ix, just that k equals to I. And you find that it just shifts e to the ix by 1 unit. But then, what does that mean? E to the ix, so the exponential derivative, e to the ix is just cosine of x plus I sine of x, equals to cosine of x plus 1 plus I sine of x plus 1. And so, e to the d cosine of x plus I e to the d sine of x equals to cosine of x plus 1 plus I sine of x plus 1. And here's the thing, if you exponentially differentiate a real function, you get a real function. So no weird black pen, red pen magic here. So, and in particular, you can just compare the two, and you get that the exponential derivative of cosine shifts it by 1 unit. And the exponential derivative of sine also shifts it by 1 unit. And it's very interesting because remember there was some video on half derivatives where it said the correct way of differentiating cosine or differentiating sine is not that it's cosine, but that it's sine of x plus something, like maybe pi over 2 or something. And in this case, the exponential derivative shifts this function, cosine and sine, by 1 unit. Maybe that's a general phenomenon. Well, let's see. Let's try it out for x to the m. E to the d, x to the m. Well, that equals to the sum from 0 to infinity of dn x to the m over n factorial. And let me just give you a little example to see what's going on. What if you differentiate x to the 4th 3 times? Well, it's 4, or maybe twice, I think. Then it becomes 4 times 3 times x squared. 4x cubed, x squared. And in particular, what does that mean? It's just, you just start with 4, you multiply it by sort of 4 factorial, but just the first 2 terms, and here you do x to the 4 minus 2. So here becomes 4 times 4 minus, so let's see, 1. Sorry. What I meant was 4 minus 2 minus 1. And x squared is just becomes x to the 4 minus 2. And so what I'm trying to get at, in general, if you do x to the m and you do it n times, it's the same thing. This whiteboard is becoming very dirty. So what happens here then is that we get sum from 0 to m, because if you differentiate x to the 4th more than 5 times or something, you get 0. That's why the sum stops at m, and what do, you start with m, and then n minus 1, dot, 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 up to m minus n minus 1. Okay. X to the m minus n. And remember, you still have to divide by this n factorial. Okay, but this is a very complicated expression. But notice, this is sort of the start of a factorial, because you do m times n minus 1, except you stop at n minus 1. So what this becomes is just m factorial times the rest, which becomes m minus n, m minus n, m minus n minus 1, n minus n minus 2. So you can verify that it's the same thing as m minus n factorial over n factorial, x to the m minus 1, n minus n. And you get that it's a sum from 0, not infinity, but m, of m factorial over n factorial, m minus n factorial, x to the m minus n, sorry, like that. I'll get to that in a second. All right, but the nice thing is, this is some term that might look familiar. Well, it's precisely m choose n. So, Pikachu, I choose you. In this case, exponential derivative m choose n. So we get the sum from 0 to m of m choose n, x to the m minus n. And here's just one little thing I want to add. Let's add 1 to the n. And the reason this is important is because now we can just use Pascal's, the binomial formula, which says that this is precisely 1 plus x to the m, which becomes x plus 1 to the m. In particular, the exponential derivative of x to the m just shifts it by 1. And this is ultra important because now I'm claiming that for most functions, it actually just shifts it by 1. Namely, for any function that has a Taylor series, what's called an analytic function, in fact, the exponential derivative is just the function, but shifted by 1 unit. So, maybe I think example 5. So suppose f has a Maclaurin series. So suppose f of x equals to the sum from n from 0 to infinity of fn of 0 over n factorial x to the n. Most functions that are infinitely differentiable have this property. By most, I mean most of the functions you encounter, but not all of them do. There are functions that are, very smooth, infinitely differentiable, but cannot be written as a Taylor series. The most prominent example being this function at 0 here, and at 0 it becomes e to the minus 1 over x squared. Surprisingly, this function at 0, the Maclaurin series is 0. So that's something for another time. All right, now let's see what happens if you apply the exponential derivative. So e df becomes the sum from 0 to infinity fn of 0 over n factorial e to the d x to the n. And that's the sum from 0 to infinity of fn of 0 over n factorial of x plus 1 to the n by what we just shown. Okay. But this is just the same. If you look, f has this Maclaurin series. Now just replace x by x plus 1 and you get that this is f of x plus 1. Cool. So indeed, for any function which has a Maclaurin series, this weird exponential derivative just shifts it by 1 unit. Lastly, what I want to say, and we may ask, is there a product rule for exponential derivatives? In fact, there is, and it's very neat. It's in fact much neater than for the product rule for the reg calculus. Okay, so let me show you the product rule. So let's calculate the exponential derivative of f times g. Well, that's the sum from 0 to infinity of the nth derivative. So dn of f times g over n factorial, which again, let's just write it in the usual way. 0 to infinity of fg, the nth derivative, over n factorial. And here's the nice thing. Now we can apply the product rule, the regular product rule for nth derivatives, which is surprisingly similar to the binomial theorem. So that just equals then to sum from n from 0 to infinity, and then, well, I guess sum from k from 0 to n of n choose k. You differentiate f k times, and you differentiate g n minus k times. And remember, we still have this n factorial. All right, let's continue. So that is then the sum from n from 0 to infinity, sum from k from 0 to n of fk g n minus k. And here's the thing, n choose k over n factorial simplifies. N choose k over n factorial, that's n factorial over n minus k factorial divided by n factorial. This cancels, and you get 1 over n minus k factorial. And so, you just put it here, but sort of distribute it, match it with the function. So it's fk over k factorial and n minus k factorial. Okay, very good. And now what we want to do, we want to interchange those two sums. It's the analog of Fubini, but for sums. And again, assume we can do that, assume we're in the legal zone. But look, what does that mean? So, suppose here is the n direction, and here we have the k direction. Then what I'm saying, first of all, n goes from 0 to infinity, so that's fine. But for k, you can only sum up to n. So from n equals to 0, you can only sum from 0. For n equals to 1, you do k is 0 and 1, then 0, 1, 2, 0, 1, 2, 3, etc., etc. So you can only sum up to the line n equals to k. Okay, and how can we write this in terms of k and n? Well, notice, again, k goes from 0 to infinity. So that is the sum from k from 0 to infinity. But now, you can only sum of values of k above the line n. This is like saying this is a line y equals to x, and this time y is greater or equal to x. So that's why you do the sum from n equals to k. It should be n equals to k. So values of n greater or equal to k. Okay. To infinity of fk over k factorial and g n minus k over n minus k factorial. And why did we do this? Notice the nice thing. Fk over k factorial, that just comes out of the sum. And so we have the sum from k from 0 to infinity of fk over k factorial, sum from n equals to k to infinity g of n minus k over k factorial. And here's a nice thing. If you do n equals to k of this expression, sorry, that's n minus k factorial. Okay. If you do the sum from k to infinity of this expression, what is it? It's really g of 0 over 0 factorial plus g of 1 factorial, second derivative of g over 2 factorial, etc., etc. So it's really the sum, if you want, of g, the jth derivative of g over j factorial. So, in other words, this actually doesn't depend on n or k at all. So this becomes sum from k from 0 to infinity of fk over k factorial times the sum from j from 0 to infinity of gj over j factorial, where j is n minus k. So in fact, we've just done a change of variables, if you want, but the nice thing is this doesn't depend on k anymore, so pull it out, and you get sum from j from 0 to infinity of gj over j factorial times the sum from k from 0 to infinity of fk over k factorial. And that just becomes the exponential derivative of g times the exponential derivative of f. So in other words, the exponential derivative of fg is the exponential derivative of f times the exponential derivative of g. So, you see, much nicer than the usual product rule. This essentially says that fg prime is f prime times g prime. And it's a nice property. It's what's called a homomorphism. So we have a homomorphism from multiplication to multiplication. And of course, if f is smooth, then this is obvious, because it would be just fg of x plus 1 equals to f of x plus 1 times g of x plus 1. But this holds for any function, not only those that have Taylor expansions. Last but not least, just two remarks. Of course, you may ask, we've proved the product law for exponential derivatives. Is there a chain law for exponential derivatives? I don't think so, just because if you do it with just shifting, that wouldn't work as nicely. So there is no chain law. However, there's a really nice quotient law. Because, first of all, we have this nice identity, e to the fg is e to the f times e to the g. In particular, e to the f times 1 over f. Then that becomes e to the d of f times e to the d of 1 over f. But that's just 1. And if you plug in 1 into the definition of e to the d, then it still becomes 1. So careful. The exponential derivative of a function is not a constant because you're summing from 0 to infinity. And therefore, we get then that 1 equals to e df times e d 1 over f. And so e d 1 over f literally becomes 1 over e d of f. This is sort of generally true for homomorphisms, but in terms of the quotient law, this just means that, because then what is ed of f over g? Well, that's ed of f times 1 over g. So that's edf times ed 1 over g. by the product loop, okay? And now using the previous fact, we get that this just equals to E df times 1 over E dg, just by this fact, and that just becomes E df over E dg. So the exponential derivative of a quotient is just a quotient of exponential derivatives. So that's really, really nice. And in case you're wondering what are the applications of this, I have absolutely no idea. I just came up with this when I did Taylor series. There might be applications, probably in like Lie groups or something, but I think this is still nice on its own. Alright, so I hope you like this little exponential derivative extravaganza. Please make sure to like this video and please make sure to subscribe to my channel. Thank you very much.